Hey everyone, welcome back. I'm Domingos. I'm also known as DMA and appreciate when I'm called the DMA. Today we have this defined integral. It's called the defined integral because as we can see, there is limits of integration. We have lower limit and we have upper limit, A and B. And it's stated that A is equal to 0 and B is equal to 1. So we're asking us to solve this integral from 0 to 1. So it is quite complicated to solve this integral using substitution or by parts. It may even be impossible to do so. So we're gonna go back from Taylor series of certain functions. Okay, first of all, we know one thing. If we have x to the power x, let's say for example y is equal to x to the power x. If y is equal to x to the power x, it's not mistake if we say Euler to the power y is equal to Euler to the power ln of x to the power x, because it's actually the same thing. It's not a mistake. If we say y, if we say y is equal to this expression, because ln is log of the argument to the base Euler, so they will cancel out. So if y is equal to this expression, because the base of the ln is Euler, will cancel out, and y is equal to y, so we can conclude that this implies that x to the power x is the same thing as Euler to the power, this x can come at the back, x ln of x. So that means they are actually the same thing, because this is y, so they are the same thing. So finding the integral of this expression, then it's the same as finding integral of that expression, because they're actually the same. So which implies we have integral from 0 to 1 of x to the power x dx is the same as finding integral from 0 to 1 of Euler to the power x ln x dx. Okay, now if we look here, we can't apply substitution or by parts here. So what we can do here, we can go back to Taylor series. Okay, since we have Euler, let's remember ourselves that we know that Euler to the power x is equal to 1 plus x to the power 1 over 1 factorial plus x squared over 2 factorial plus until x to the power n over n factorial. So since this is a sum of many terms, it's the same as saying that this is summatory from n to 0 until infinity of x to the power n over n factorial. But the thing that we realize here is that we don't only have Euler to the power x times ln x. We have Euler to the power, we don't just have Euler to the power x, we have Euler to the power x times ln x. So this theorem can't be applied here. But if you want to find the Euler of x times ln x, just substituting where we have x by x ln x. So, which implies that Euler to the power x ln x will be equal to 1 plus, where there is x now, we'll substitute by the exponent. So, which is x ln x over 1 factorial plus x ln x squared over 2 factorial plus, where there is x, it's x ln x to the power n over n factorial, which is equal to this expression from n summatory of n from n equal to 0 to infinity, where there is x, will be x ln x to the power n over n factorial. So now, if we know that this expression is equal to that expression, then we can replace back. We will have integral from 0 to 1 of this expression can be that expression, summatory from n equal to 0 to infinity, x to the power ln x whole to the power n over n factorial. Now, what we can do? N factorial, since we're derivating with respect to x, that means any other variable different than x is considered to be constant in this case. So that means n factorial, this summatory, they can come outside because they're constant. So we're going to have integral from 0 to 1. Let me just start by writing the constant, which is summatory from n equal to 0 to infinity 1 over n factorial integral from 0 to 1 x ln x to the power n dx. Okay, now to solve this integral, we can take our ln of x to let to be equal to something. So we can let, in this case now, we can let that ln x is equal to minus t. So we can let ln x to be equal to minus t. So if ln x is equal to minus t, what's x? Isolating x according to log rule, it's going to be Euler to the power minus t. So since we're dealing with integral, we have to differentiate both sides to find what's the value of d of x. So differentiate x, what's the derivative of x is 1, so it becomes dx equal, the derivative of Euler, it's going to be minus Euler to the power minus t dt. That's the result that we get. Now, since it's defined integral, it's not undefined integral, we have limits of integration. So we have to find now what's the value of t, because we are implementing new variables. So these limits of integration was for x, 0 for x and 1 for x. But now since we're introducing t, we have to find what's the value of t when x is 0. So when x is 0, we will have ln of 0, which is minus infinity. So we're going to have for x equal to 0, we're going to have ln of 0 equal to minus t. And the ln of 0 is negative infinity equal to minus t, which implies that t will be plus infinity. Okay, so what happened now for x equal to 1? For x equal to 1, we're going to substitute back ln of 1. So ln of 1 equal to minus t. So ln of 1 is 0. That implies that t definitely will be equal to 0, because 0 times minus 1 will still be 0. So that's going to be the value for t. So we have t, 0, and t plus infinity. So that means this integral will be rewritten as integral from 0 to infinity. Where there is x, we said it's a Euler to the power minus t times, and where there is ln x, we said to be minus t, all these to the power n, and dx we set to be minus Euler to the power minus t dt. Okay, now remember this expression, this integral is for this integral. There is still the outer part, which is this sum here. So we can include here, which is sum from n to 0 till infinity 1 over n factorial. Okay, perfect. Now, so what is going to happen now? We have this expression negative, and we have this expression to the power n. We can separate them. So this implies that we're going to have this expression 1 over n factorial. This is going to be integral from 0 to infinity Euler to the power minus tn times, this is minus t to the power n, which can be written as minus 1 to the power n times, we can say this is t to the power n, because when the exponents are equal, we keep the exponent, we multiply the base, so that goes back. And now here we can say it's times minus 1 times Euler to the power minus t dt. So this is gonna be 1 over n factorial. Now integral from 0 to infinity. Now if we check this expression, minus 1 to the power n times minus 1, it's a constant, so it can come outside, so it will be minus 1 to the power n plus 1, because the base are the same, so we add the exponent. Now we have t to the power n times, for the Euler, we have Euler, we add the exponent because they're multiplying, so we can have minus n plus 1 times t dt. Okay, so we can have that expression there. This is what we have. But this improper integral reminds us Laplace, but what is missing is like Euler to the power minus st to be Laplace transform. Here we can let, from this expression, we can let n plus 1 to be equal to, in this case, to be equal to s. Why s? Because this will transform into Laplace expression. So we're going to have the summatory n to 0 minus 1 to the power n plus 1 over n factorial integral from 0 to infinity of Tn Euler to the power minus st dt. So this reminds us Laplace transform of t to the power n, which is equal to n factorial over s to the power n plus 1. But the thing is, we were not given this problem in which respects to s. I mean, we were not given in which respects to s. So that means we have to substitute backwards the true value of s, which is n plus 1. So this will be equal to n factorial over n plus 1 to the power n plus 1. So then the final answer will be minus 1 to the power n plus 1 over n factorial times n factorial over n plus 1 to the power n plus 1. They cancel out. N equal to 0. Minus 1 to the power n plus 1 over n plus 1 to the power n plus 1. Okay, so this is the solution of this integral. So if you enjoy, leave your like, your comment, subscribe, and most importantly, share with your friends.